Hi all, welcome. It is my great pleasure to have Professor Falk Amelung present at the CAE Spring 2025 seminar series. Professor Amelung is a professor of geophysics in the Department of Marine Geosciences at Erasmus at UM. He received a PhD in seismology from the University of Strasbourg in 1996. After a few years at Stanford University and the University of Hawaii, he joined the University of Miami in 2002. His research group primarily uses space geodetic data derived from Interferometric Synthetic Aperture Radar, InSAR, to study active volcanism, tectonics, and land subsidence. The title of the talk is Coastal Subsidence on Miami's Barrier Island. This talk has, and the associated work has received a lot of interest from local and other press. So thank you very much, Professor, for your time, and we look forward for your talk. The floor is all yours.
Okay, thank you very much, Pranoy. Yeah, so it's a pleasure to give this presentation. So as Pranoy said, normally I'm a completely different geologist. So I'm studying volcanoes and tectonics using this satellite technique. And yeah, so the work what I'm presenting here is was mostly done by Fazane here. She was a postdoc with me, and now she is at Washington University in St. Louis. Okay. Okay, does this work? Yeah, it started with this 3.5 years ago. The condo Champlain Tower South in Surfside collapsed out of nowhere. It looked like, and yeah, me studying or my group studying earthquakes and volcanoes, everything what is related to studying all kinds of disasters. So what we were hoping is, what we wanted to do is to investigate whether the structures like the Champlain Tower South, whether it can be monitored with satellites. Can we see some precursory displacements that could be indicated to give a warning? And what is the role of the local geology? Could the local geology have played a role for the collapse? And yeah, the collapse itself, for those who are not aware of it, it was just poor, well, tragic. 98 people got killed. It was the result of poor maintenance. They didn't do any. They knew they had to do repairs, but they didn't have the money, so it didn't happen. It's really, really very tragic. So the technique, what we are using is interferometric synthetic aperture radar. This diagram displays the principle. We have a satellite flying over the Earth, sends a signal. This signal goes back to the satellite. We are getting from trees, not necessarily signals, but mostly from structures. Now, 12 days later, the satellite comes back to the same location, and we see a slight displacement. If there's a slight displacement of the ground, then this will be somehow recorded. Another 12 days again later, it comes again to the same place in space. And so if the ground is stable, we don't see anything. If it has moved, we can this is going to be recorded. The way how the data processing works is, we are doing something what we call an interferogram. So the satellite image has a phase. It's an active imaging instrument, radar, synthetic aperture radar. It has a phase and an amplitude. We combine the phase of two images to form an interferogram. This is an example from a volcano in Hawaii. Here we have for example, an interferogram between two images. We are doing lots of those interferograms. We're having a network of interferograms, and then we are doing a big geophysical inversion, mathematical inversion to retrieve the time history of displacement. And that is shown here for an example of a volcano in Hawaii, actually Kilauea. The green dots is the InSAR. The black is a GPS station, and so it agrees as it should. The signals, what we have is we are considering persistent and distributed scatterers. The persistent scatterers, that is something what acts, we'll talk about it some more later, what acts as a corner reflector. It just reflects the signal back to the satellite, houses or something on high rises. And then we also have distributed scatterers. That is more shallow surfaces like roads where the signal or radar signal is not from one single scatterer, from the sum of multiple scatterers. And persistent scatterers, also they are point scatterers, they have a much stronger signal. And then we have other areas where we have vegetation or no persistent scatterers, no distributed scatterers, where we don't get any signal. This technique is computationally pretty expensive. We are using the Texas Advanced Computing Centers. If you want to process one data set, so it's maybe something like 2.5 or 3 terabytes of data, and it can take quite a lot of disk space. And so then there's a couple of different softwares what we use for the analysis, for the final analysis. In this case, a software which was developed actually by a student in Hanover called Survey. To give you some background on Florida, well, Florida, or on the geology, on the geologic background, Florida, of course, we don't have much topography, especially not down here in the south. If you go to the north, there's a little bit of topography, and if you display it as a shaded relief, then so it looks like there is some topography. We are looking at the Florida platform. This is the entire Florida platform. 20,000 years ago, during the last glacial maximum, Florida was much bigger. This was the spatial extent. 120,000 years ago, that is when sea level was a little bit higher. Florida was much smaller, and that it's going to so during this time, 120,000 years ago, South Florida was inundated, and the Miami limestone was deposited. So we are sitting here on the Miami limestone. Underneath there is, and that is relevant for the geology later on, underneath is something what is called the Anastasia Formation, which was deposited during the previous sea level high stands. We are on the platform, so the geology at depth is quite messy. The currents change and these kind of things, so it is very hard to predict what exactly we have under the Miami limestone. And in Surfside, we are on a barrier island, or in Surfside, in Miami Beach and Surfside, we are on a barrier island. So we have the coastal ridge, the Atlantic coastal ridge over here, which is formed which is directly the Florida, the Miami limestone, and then the barrier islands to the side. So how does the Miami limestone looks like? In downtown, there's a few places under the metro rail where you can see the limestone. In some places, it looks like this. This is what we would expect. But in other places, the limestone gets pretty messy. It has lots of wax and voids. That's partly related due to creatures which were living at the time, and they essentially ate the limestone. And so it is a little bit, we don't really know exactly where we have what kind of limestone in the underground. And we are on the barrier island. How does a barrier island look like, or how does a barrier island form? It forms by the coastal currents. Coastal currents, they transport material. Originally, it was quartz sands brought from the Appalachians. In the meantime, it has been, new sands have been brought in. The barrier island developed over the last 5,000 years when the sea level was relatively stable. But barrier islands are not stable. They grow and they wax and wane depending on the currents. And so sea level rise is of course a great concern for Miami. And another question is land subsidence. In the last couple of years, a couple of studies came out looking at land subsidence along the East Coast. Couple of areas there were detected something like 3 to 5 millimeters of subsidence. This study actually has the data analysis is not easy. So this study has actually quite a lot of problems. I don't believe everything of it. But in Florida, it's mostly green. Green means there is essentially no subsidence going on. And so that's what we thought before we did this study. A couple of years ago, Szymon Wrowiński, who used to be at also before he moved to Florida International University, he was in our group. He did a study with a student looking at land subsidence in Miami Beach, and he didn't see much. Everything is green except a few areas. Few areas are yellow. That are areas. So this is data from the 90s. Very old data, and he had something like 23 images or something like that, not more than that. There is not much subsidence going on, except up here where the Champlain Towers south is. So that's really striking, surprising. This was done before the Champlain. He had no idea that obviously the Champlain Towers south are going to come to collapse, and there was some subsidence detected in the 90s. So now we are looking at the recent data. This is how a satellite radar interferogram of South Florida looks like. Most of the single one of those color fringes corresponds to 2.8 centimeters of displacement. 2.8 centimeters, it could be because of tropospheric delays, because of water level changes, and because of ground deformation. So here it's a zoom in into one interferogram. So this is one interferogram. Later on, we're going to combine something like a total of 1,000 interferograms or so. So that is one interferogram for the Miami Beach area, and this is the result essentially of our study. So it's now the result of 220 images up to 23 starting in 2016. Then that is when the satellite, the good satellites, European satellites, Sentinel-1, when they were launched, and most of it is green. Green means zero displacement, but we have a couple of areas where we have blue dots, and these blue dots indicate subsidence. Subsidence of up to 0.6 centimeters per year, not very much. We are having 7 years of data, so the maximum what we saw somewhere is 8 centimeters of displacement with this satellite. So the blue dots, we have them in Sunny Isles Beach, here strong blue dots, then in Bal Harbour and Surfside. In Surfside, the collapse happened down here, but really a strong blue dot area, subsidence hotspot, is actually the surf club area. And then we have Miami Beach. There, surprisingly, is hardly anything. We have 2 buildings which are subsiding. So I'm going to go through one of those data in more detail. So these are all the high rises in northern Sunny Isles Beach. We are getting data only once a high rise is completed. So before that, nothing is persistent. We don't get anything. These high rises, while being constructed, you can get up to 30 centimeters of subsidence settlement, as you engineers say. We are getting the data only once the structure is there. So for that reason, we are looking at two different time periods. Some of, I'm not going to go into detail. Sometimes it is 2016 to 2023. That is for persistent scatterers, which are persistent during the entire time period. And for other buildings, we are looking at a shorter time period starting in 2019. And okay, so how do these signals look like? So here, for example, for the Ocean 3, it was pretty stable at the beginning. Then suddenly there was some subsidence of 2 centimeters over a 2 or 3 year time period. And after that, subsidence continues at a slow rate. The Porsche Design Tower, we have, in this case, since 2019, we see 2 centimeters of displacement. And so let me give you an introduction. While nobody in the audience is living in one of these buildings, I suppose. These are really luxury asset bests in the Porsche Design Tower. There's an elevator for your Porsche. If you're living up there in the 53rd floor, you don't have to deal with parking your Porsche somewhere. You just put it right next to your apartment. Beautiful views, of course. You need your own pool with a great view of the bay, and so these places are not cheap. The tax bill, something like $350,000 per year. You're getting an 11-car garage, what of course is absolutely needed on the 53rd floor. And there are some famous residents. For example, Lionel Messi, when he came to Miami, when he arrived here, he first lived there. Now he's living somewhere else. So for the Porsche Design Tower, what type of measurements do we get? Where do we get the measurements? So this is how the Porsche Design Tower looks from the top. We are having those, there's all kinds of structures, smaller scale structures, and they act as persistent scatterers or as corner reflectors. So the satellite comes and looks, the radar signal comes against that, and then it gets, if there's a structure which is having exactly the right orientation, perpendicular to the look direction of the satellite, it reflects the signal back to the satellite, and then we are getting a measurement point. That is a persistent scatterer. And if you also what acts as persistent scatterers on the ground, for example, at the side of a boardwalk or a small wall like that, the satellite sends its signal. It might get reflected twice, then it goes back to the satellite, and so in some points they do act as persistent scatterers. So if you're taking your morning jog along the beach, the satellite is imaging you. Okay, let me go over some of the other examples. So in Sanibel Isles Beach, there's really signals all over the place. I think a total of 70% of the buildings show subsidence. Not very much, couple of centimeters. Here we have something which is more or less linear. Here, the pinnacle, there is an interesting signal. It stopped, then it continued again. Here, the jade, there is an acceleration of the displacement, so we see it at lots of those buildings. I'm going to go over this in. So this is now Bal Harbor and Sunny and Surfside. In Bal Harbor, surprisingly, we don't see much subsidence. There's largely one building, the Oceana, in Surfside, we see quite a lot. And in particular, near the surf club hotel, there's significant, something like 2 or 3 centimeters of subsidence during a certain time period. And yeah, the Arte residence down there was relatively recently built. We have a signal there, and also of the 87 Park Tower right south of the collapsed condo. In Miami Beach, as I said before, hardly anything, but most of the buildings there are older. Recently built condos are just the L'Atelier condominium and the Finer house. We do see subsidence there, though not very much, less than 1 centimeter over the 7-year time period. The Finer Forum is another structure which was recently built. There we have no scatterers, and if you look at the shape of this building, this is not really a surprise. There's nothing what acts as persistent scatterers. So to summarize this, in Sunny Isles, we have about 70% of the structures which show subsidence. In Bal Harbour, just 3%. In Surfside, about 20%. And in Miami Beach, just 1 to 2%. And always between 2 and 8 centimeters. So let me give you, so these calculations, these measurements, it's not easy. Let me explain a little bit more, and it took a long time until we were convinced that this is correct, and we were able to publish it. Let me show you an example for the Oceana residences. So the satellite map looks from the left side, and the pixels, they show up to the left of the building. So why is that? We are using a digital elevation model, but that doesn't have the Oceana residence in there. That's very, very complicated to do. So the signal, the satellite looks, the first signal, what comes is maybe from the rooftop, and whether we are getting a signal there from the rooftop or from well, the same pixel could be from the rooftop or could be from the ground somewhere there. So that is the reason why it shows up over there. And that is somehow not easy to deal with. But so what we do then is we estimate the elevation from the synthetic aperture radar data, from the InSAR data. And so in this case, this is all red. Here's the color scale for the elevation. That's something like 70 meters or 80 meters. And we have a digital surface model of the area. Yes, the Oceana residence, they are about 80 meters high. So that gives us some confidence that these pixels, which don't show up on the roof, that they are actually located on they are rooftop pixels. So then what we do is we correct the location using this estimated elevation. So then what we are ending up with is something like that. This is a velocity, but this looks surprising. So all these blue dots, they ended up right here. And then we have also some green dots, which we had before. The green dots mean no displacements. So could this be 0.6 centimeters per year differential settlement? That would not be good. Hard to believe that that's what it is. So how does the geo-corrected elevation looks like? Some of those pixels, those which moved over here, are at 80 meters high, but we have a couple of others which are at 20 meters or something like that. And if you look at the structure, there is the opening over there. So these light green dots, which don't move, which have low elevation, they are somehow reflections within this opening, or they don't represent the displacement of the building, they represent the displacement of the ground somewhere nearby. So that gave us some confidence that all these results can be believed. And still, we wanted to be very careful. We don't want to publish anything which we are not certain about. So what we did is actually we looked at, we used different software. We got some colleagues on board. They used the commercial software called SARPRODS, and they see more or less the same time series, the same displacement. Not 100% the same, and that is there's some different filtering algorithms used, and they didn't actually look at exactly the same time period. But so we were happy. And also then we used a completely different satellite, TerraSAR X, a German satellite, and we see essentially the same signal, not 100% the same, because this satellite actually looks from the other side. Here we are looking from the west, and this satellite looks from the east. So the persistent scatterers are different, but still the same signal. So we are very confident that all these results are correct. And NIST in the National Institute of Standards and what is it called, technology, I believe, they did published a contractor report. They looked at InSAR data, not this way as we did, at lower resolution, and they see settlement at some places. And so this technique is used. It was used, for example, by one of our co-authors to study a bridge collapse in Genoa in Italy, and even the Kharkovka dam failure in Ukraine. So yes, we can, if everything is properly checked, we can trust those results. So let me talk in more detail about some of those observations. Here, there's the Surf Club in Surfside. The collapse condo is 500 meters to the south. Here you see the old structure, which is the old Surf Club, and there is a new structure on top, built in 2016. And this is our blue, one of our subsidence hotspots. There was something like 2-3 centimeters of subsidence in 2017, but the result is somehow surprising. There was little at the beginning or nothing, and then suddenly it starts. So it's hard to explain. There was a new structure built in 2017-18, the Arte residence. This image when this image was taken, it didn't exist yet. So could be that this is related to construction vibrations related to construction of the Arte. Another thing which was somehow is striking. So this is a subsidence hotspot. The Surf Club was one of the first areas in Miami Beach. There were already some hotels in 1935, but in the northern part of Miami Beach Island, this was the first hotel. So what we thought is maybe there's something special in the geology just there, and that was the reason why they built the hotel over there. And maybe that's the reason why we have so much subsidence right at this location, but we didn't find any evidence for that. So what are the causes for the subsidence? We have, for a few places, we have geotechnical exploration reports. Unfortunately, just for a few. If we had more, our study would be much more conclusive. But we have just for 4 different places. For the Porsche Design Tower, and in the Porsche, so what do we see? At the top, the yellow area is sand. That is essentially the barrier islands, the upper 5-7 meters or so, deposited in the last 5,000 years. The gray colors indicate limestone. Much harder limestone. And then in the north, in the Porsche Design Tower area, and also this is for Surfside. So there's a couple of sand layers, much more sand layers in the north than in the south. But it is not really statistically representative, as we don't have much of those information. So we have more sandy layers and construction in the north, and then okay, I didn't finish this slide. We have the N values from the standard penetration test. The N values so the standard penetration test, the engineers, of course, know it. What is done there is you essentially hammer into the ground, and you see how much hammering blows you need to get through the ground. If it is hard rock, excuse me, if it is hard rock, you need to hammer much more frequently than if it is soft rock or sand. So there are some areas here where the N value is very high, so it's very strong rock, and then we have something weak. And here we have, again, a few layers, much harder. For the 87 tower in Surfside, it seems to be pretty weak, up to 30 meters or so, 25 meters. But in any case, more sandy layers and more construction in the north. So, and then we have some more information about the geology. The USGS, United States Geological Surveys, they did some drill holes in Miami Beach, Stillwater Park, and Fisher Park, and they do proper geologic investigation. This information is available online. That is great. Without this, we wouldn't have been able to do this study. And we see some surprising results. Stillwater Park, there's actually a void in 50 meters, a half a meter thick void. At greater depth, there is pretty strong limestone. In Fisher Park, there is, it's a good example of the sandy layers. These sandy layers, quartz sands brought from the Appalachians long time ago before the Miami limestone was deposited. At other places, we rather have, we have just limestone. For Miami Beach, not for Surfside or Bal Harbour, we have some sediment cores. This is how they look like. So the limestone does have some holes. Other limestone is a little bit stronger. We only have pieces in between. Things are missing, and that is most likely because there was sand, and when they took the cores, the sand washed away. The sand is what we really need, but I'm going to come to that in a minute. Okay, so what could cause the subsidence? Typical explanation for land subsidence is groundwater extraction. In this area, there's no groundwater extraction. Then it can be consolidation. In places, according to Terzagli's principle, that is happening, for example, in Chicago, where the high-rises are built on fields. The sill or the clayey rock contains, or sediments, not necessarily rock, contains water. This water is essentially pressed out when you put a heavy building on top of it, and this pressing out can be a slow process. But in the limestone of Miami, no, this is not happening. Terzagli's principle is not relevant. Then we can have natural compaction under the weight of the structures. And yes, that's happening during the construction phase, the settlement during the construction, but we are looking now at data many years after the construction. So there we wouldn't expect that the natural compaction under the weight of the structure continues. And the last possible explanation is construction related. And yes, so that's what we think is happening. So our hypothesis of what's going on is, you're building a high rise on the barrier islands. In the top, we have the sand from the barrier island, and then we have the limestone with interbedded sand layers. So the sand layers, in the sand, the packing before construction, it might be like this. So it is, somehow randomly oriented, the sand grains. So now there is some vibrations, some construction nearby with strong vibrations. And so you're moving, these sand grains are exposed to the movement, to the seismic waves, and then they are moved in one side. And then, yes, the seismic waves, then it goes other way around, they are moved to the other side. And if this happens quite frequently, well, if this happens, then you're ending up at the end with some compaction. So the sand grains are arranged, the sand grains got rearranged, and now it's much more efficient. It takes less volume. But so yes, that is we know that this can happen. But so now to what I know in the last couple of years, they are not vibrating very much anymore for the construction. So, but there's other mechanisms. For example, they do have to pump for the construction of the foundation, at least for some part of the foundation, construction of the foundation. To what I know, we can talk about that later some more. So if they pump, then yeah, they're pumping like crazy, and then the water flows towards the pump, and the pretty heavy flow through the sand through the limestone, through the sand layers, and that can have a similar effect as the very similar effect as vibration. So you might be able to rearrange the grains through the water flow by pumping. And okay, let me just show an example of the vibration effect. This is my morning tea. It gets denser packing. And granular material can have some strange behavior. I don't know much about it in physics and material science. They're working on that. I would like to know some more, but yeah, there's some granular material here, an experiment, a study which was done 10 years ago. There's very little bit of vibrations, and very tiny, hardly to measure. But this is still enough that yeah, this what they put on there can go into the sand. Okay, let's talk a little bit about the spatial patterns and the temporal patterns of our observations. So in some places, we see very localized subsidence. And this is, for example, for the 87 park, just south of the collapsed condo. Our blue dots, so this is now using the distributed scatterers. The measurements are a little bit less reliable, but in this case, only here, nothing else nearby. In other parts, we see, okay, we have the dark blue dots and we have the lighter color blue dots. So their subsidence seems to be extended over a larger area. A possible explanation is there is a spatially extended sand layer, and the entire sand layer, everything what is over the sand layer subsides a little bit. Spatial correlations are a little bit difficult to explain. The temporal patterns are more straightforward to interpret. The Ritz-Carlton residences, for example, in Sunny Isles Beach, they show a nicely exponential decay. It was completed, that building, in 2019, and yeah, so what we probably see is an after effect of its own construction. But so yeah, the geotechnical engineers, they say, oh, well, this is a new building. You expect subsidence settlement during construction, and in the geotechnical reports it says for a couple of weeks after construction, but we see for 5 years later. So an after effect of its own construction. Right next to it, we have the Trump Tower 3, and it subsided a little bit, and then suddenly subsidence, fast onset of subsidence, and then it was pretty slow. So this is located right next to the Ritz-Carlton residence. So possible explanation is that this subsidence is somehow related to the construction of the Ritz-Carlton. Would be nice to have vibration information or what exactly they did, but unfortunately we don't have that. The Oceana, about which I mentioned before, okay, it was finished in completed in 2016. Initially exponential decay of the subsidence, but then it is more or less linear. A clear example of linear subsidence is the regalia. though it is not going very fast, something like 1.5 centimeter, but there's not really an indication for this slowing down anytime soon. So how could we get this more or less linear signal? Possible explanation is this is complete hypothesis. We have no evidence for it, hypothesis, as I said, grain rearrangement by tidal flow. So we at the coast, the tidal water goes through the sand layer. The tidal flow goes through the sand layer twice a day. It goes up, it goes back and forth. So this could result in grain rearrangement, as I showed before, in a similar way as construction vibration. And then another possible mechanism is dissolution of limestone from stormwater injection. And what do I mean with that? On the barrier island, okay, we are over here. There's quite a lot of, well, under the barrier island, there's a limestone with some sand layers, and there's salty water. The limestone is saturated with salt water. And then we are injecting fresh water, storm water, just to get rid of the flooding. And so there's lots of those stormwater wells. This is for Surfside and Bal Harbor. And that's a potential mechanism. In principle, it's not a good. So what you can get is, as a result of these two things, the water, if it's put in under pressure, then it may rearrange the sand layers, and then you get potentially dissolution of the limestone. Dissolution of the limestone is a very slow process, but here we have mixed water, fresh water, and salt water, and that is more efficient. It is still supposed to be a very small effect. You wouldn't expect more than a millimeter per year, but maybe there is something what we don't understand yet. That is certainly something what should be studied in more detail. So what about differential settlement? So what I showed up to now is that the whole building just goes down by itself. It's not it's annoying. Sea level rise, it may exacerbate flooding related to, but it's not really a big problem for the structure. Differential settlement would be a problem. So we haven't looked at it very much in detail. We don't see much, but we do see a little bit. And there's two examples here. One for the Surf Club Hotel. We have 2 pixels which are estimated to have exactly the same elevation, and there's a 0.3 centimeters per year difference. If this continues, that can eventually cause problems. And similar for the 87 park, there could be some differential. There are some indications for differential settlement, and longer time series will show whether this continues. What about tilt? Okay, what we say in our study is that we are seeing only up to 8 centimeters of displacement, but actually it's not quite true. That is something what came while the study was done, and we are not talking about it very much. We see for the Porsche Design Tower actually 11 or 12 centimeter using the higher resolution satellite, which we got only later during the study. So that is so this is now from descending satellite images. So in this case, the satellite looks from the coast. Earlier, what I showed was from ascending satellite images. The satellite looks from the different side. So a possible explanation. So for a pixel near the roof, 11 centimeter in descending, 5 centimeter in ascending. A possible explanation is actually that this one is tilted slightly towards the ocean, tilted inland, but only very tiny. So not really anything to worry about, not at all. it does agree with the easterly winds. So, but we have clear evidence for this just because we didn't look only for the Porsche design tower. So to summarize our data, these are the buildings for which we see subsidence. These are the average velocities over the 8-year or 7-year time period, and yeah, so some of those structures are high down in surfside. The structures are not so high. You're allowed to build only 12 stories. Still, we are seeing quite some high subsidence rate, and the normalized velocity, that means velocity per height, is higher over there in the south, which could indicate well, in the surfside area, which I think indicates more sand. What is about the age of those structures? What we are looking at? We don't see subsidence only for new structures. 20 of those structures were built before 2010. We have only 7 years of data, but yeah, if the subsidence, there's a scale missing, if the subsidence was going on at the same rate, so a couple of centimeters per year for a longer time period, then yeah, so that's a little bit a reason of concern. What about the collapsed condo? This is a yeah, Champlain Tower South. We do have some pixels which go, and we have here shows the data up to exactly the collapse. They don't show any signal. Completely, yeah, no signal. The radar though is looking from that direction. There was evidence for precursory cracks under the pool deck or on the pool deck in this area, and that is something what we can't observe with our satellites. It's just in the radar shadow. Surprisingly, well, we have the 87 park right next to it. We know that there was significant vibrations, really strong vibrations done while the 87 park was constructed. So we really would have expected to see some subsidence, at least a little bit during the construction of the 87 park, but we don't. The 87 park itself, though, is subsiding. So these are not really conclusive. What is about other parts of Miami? There is quite some signals in downtown Miami. We haven't looked at it in detail at all. There, the analysis is just much more complicated because you have to figure out from which building the signal comes back. In summer, I visited China, and well, they have high rises all over the place in China. And yeah, now when I go into a high rise, the first thing I do is I process the data, and there's lots of blue dots, actually quite significant, up to 20 centimeters, 10 centimeters or so of subsidence, and we don't. Yeah, so there were some cracks even in some of those buildings, but people know it. They are steady. There's no concerns that they are going to collapse anytime soon. And yeah, if you look at how those buildings are built, very strong foundations. So these engineers, they really know what they're doing. Very strong foundation, incredible amounts of concrete. So yeah, they are not going to collapse anytime soon. I have no concerns. A couple of weeks ago, I happened to be in Sri Lanka. Yeah, there's a skyline of Sri Lanka, and lots of high rises. So then I looked at the data, and I didn't see anything. These high rises, they are socketed into crystalline metamorphic bedrock. So if you really have strong bedrock, stronger bedrock, not limestone. Well, limestone is pretty strong, but this is crystalline metamorphic bedrock. That's probably the reason why there is no indication for subsidence. So, and is this tilting, what I showed before, a problem? Not really. There is the tilting tower, it's well known, of San Francisco. It was poorly designed. up to 70 centimeters of tilt was found, but the structure is still standing. The tilt can be, they're trying to repair it. Some other towers are tilting since a very long time. That's the Leaning Tower of Pisa. We did look at some other places in Miami-Dade, but this didn't go into the paper and has to be analyzed more carefully. A couple of years ago, the Broward County Courthouse was closed because they found cracks. You can see the cracks over there. This is a structure where we do see a signal. So maybe, yeah, it's, well, maybe part of the signal is related to these cracks. A really strange signal, we see it close to in Broward, to the Taylor Birch State Park. There's the state park here, and there's a small subdivision, and there is some significant subsidence happening starting in 2021. Significant, not really. Couple of centimeters. It was stable up to then, and then it happened. And we didn't get a chance to investigate that in detail. There was some seawall repairs, maybe some vibrations, and then, yeah, what is surprising with all these signals, what we see, you have the vibrations only for a short time period, but then the subsidence, it instigates a process. Subsidence continues for quite a long time. So to summarize, we're having 2 to 8 centimeters of subsidence. And we do see it at quite a lot of older structures, pre-2010 structures. It's caused by grain readjustment. That's what we think, related to the construction vibrations. That is sort of, not necessarily a surprise. But then there's also other possible causes: construction pumping, tidal flow, and stormwater injection. And that really requires more investigations. And the Champlain Tower South, we don't see anything. I didn't mention it, but that we are on a barrier island has no influence. The geology was affected. This is not the barrier island geology, is the geology at greater depth, which was deposited earlier, in earlier time. Is there a climate connection to these observations? Not really. At least not a clear one. If stormwater injection and limestone dissolution plays a role, then yes, there is somewhat a climate connection. We are getting more and more rain. Limestone is going to be dissolved faster. So what we are hoping to do in the future, but at the moment we have no funding. I'm not sure whether this is going to happen any time. We want to look, of course, at other places. It would be really good if we had those geotechnical exploration reports for all those buildings, a database of the geological information. That would be extremely valuable. Then we could compare the subsidence observations with the subsidence observations with the local geology. We hope to do eventually the seismic experiments. You can do it using the fiber optic cables, which are everywhere in the ground for the internet, technique called distributed acoustic sensing. That would give information about how much vibration there is. We would like to retrieve the sediment cores and then really do some geotechnical testing. Wrote proposals for all this, but never got funded. And if we get a chance to do some more, what would be really useful is to check whether whether this technique can be used for monitoring the building stability. That was one of the ideas when we started this. So occasionally there's problems, or there was problems with some of the structures were evacuated. There was do we see something what could indicate from pixels on the rooftop that a structure is unstable? In principle, what I think is that all this data, what we have produced in that form, they should be available online in a database. People who live in those condos, they should be able to go and if they see something what looks a little bit like a signal, then they can check somebody to check whether there's send somebody to check whether there's a problem. And yeah, if we get a system like this, maybe eventually it could even help to lower insurance costs, which is famous, well, which of course is a problem. So the study got quite some attention in the media. One of those examples, one of this is this one. So Miami is sinking. Well, yes, the high rises are sinking, but at very, very low rates. So until we are seeing average maybe 5 millimeters per year, in 20,000 years, if this continues, you will get 100 meters, but 20,000 meters is quite a long time. Okay, with this, yeah, thank you very much for your attention. This up there, again, here's Farzaneh, who did most of the heavy lifting of this study. And this is an example of a TerraSAR X image, a higher resolution image, which we didn't really use. If we, well, we use it a little bit, but if we systematically can start using this, then we are going to be able to get much better results. Okay, thank you.